All right, everyone. Welcome back. I hope you had a delicious lunch or delicious dinner, depending which continent you're on, which continent you're watching us live from. Thanks to everyone on the YouTube for your comments, for your questions and your engagement. Thanks for watching. Big wave. Can we give a big clap to everyone in YouTube for watching? Thanks. All right, with that shout out to our online friends. Our afternoon kicks off with a chat talking about novel hardware for AGI, which I'm super excited by. It's a co-presented discussion, fireside chat between Dr. Ben Goertzel, CEO of SingularityNET, who you all know and will have I'm sure, come across already, and Rachel St. Clair. Rachel presented at AGI-21. She was possibly one of the only female speakers presenting a paper. It was fantastic to have her there. At the time, she was doing her PhD. Now she's got her PhD. So a little clap for that. Congratulations. Congratulations. Rachel's finished her PhD in complex systems at Florida Atlantic University and is now starting a new company, Simuli, working with us with Ben on AGI optimized computer chips. They're going to tell us all about it.
All right. Thanks. Oh, yeah. Yeah, we should get it that way. 40 minutes. 40 minutes. All right. So, yeah, sitting down up here feels very lazy somehow. I'll try to stay in the chair. Yeah. So, Rachel and I have been bouncing back and forth these topics for a while, and have recently started working together in practice on trying to create optimized hardware for AGI, and I want to take advantage of having such a highly educated audience to dig a little bit into the details, at least as much as we're going to do in a chat context without a bunch of diagrams and so on. But let me first briefly frame why I think this is an important and interesting thing to do. And although it may be obvious to this particular audience. So, when I started trying to work on AGI in the 1980s, early 80s, I think my first attempt at an AGI program, which failed miserably, was in 1980 or something. It was on an Atari 400 computer with 16K of RAM and the cassette tape drive. And so it pretty soon became clear you're not keeping like a human level AI's memory in there. I mean, much later, when I first started trying to implement functional programming based AI systems in Haskell in the early 90s, again, it's constant like stack overflow from too much recursion of agents creating agents. And on the whole, much of the experience of doing AI throughout the 80s and 90s was just, you have almost no memory in your system, and the processors are very slow. So what you can theorize compared to what actually will happen in your implementation is just way off. Even like, I think 89, when I was at University of Nevada, where I later met Matt Clay, who's also presenting here. We had a Cray YMP supercomputer, cost $10 million. The state of Nevada got the supercomputer in exchange for accepting a bunch of nuclear waste in the desert near Tonopah. Computer is long since trash and is outdone and powered by the GPU in my phone. The nuclear waste will be there a while, so I'm not sure it was a great deal. But I mean, that was 1,000 processors concurrently in SIMD parallel, which you program with Fortran, right? And I mean, that was cool, but still, it's like 1,000 processors, right? So constraint from hardware has been a really big issue in the history of AI, and time again, there were algorithms that actually made total sense and would have worked way better if they were just run on more data or more hardware and then tweaked a little bit with the rapid feedback you can get from being able to run quick experiments. Instead, the ideas were thrown out as being non-workable. And obviously, the example of this, which is best known now, is neural networks and deep neural nets as one type of neural net. I mean, deep neural nets have been around forever. And once you add NVIDIA and other GPU makers making these SIMD parallel hardware devices for matrix multiplication, I mean, then suddenly a lot of old ideas about deep neural networks turned out to have minor variations that actually worked really well, right? And one wonders which other good old AI algorithms that's true for in one form or another. I mean, in automated theorem proving, that's been fairly true. I mean, the best automated theorem provers can prove like 70% of theorems in Mizar and other standard corpora up beyond the PhD level. And you know, there's new things being introduced into theorem provers all the time, but not really radically new algorithm ideas very often. It's mostly just you can run parameter tuning runs over and over and over again until it works. And so I think what we've seen with automated theorem proving with deep neural nets and with more areas than I'm going to recount, I mean, I think an element of that is going to be true for AGI also. So it's, of course, not as simple as give me a faster computer, I'll run my exact code from today on the faster computer, and then it will like take over the world and utopia ensues, right? I mean, it's not as simple as that, but it's more like once you have a processor that lets the experiment that used to take a month take a minute, right? Then you can run many of those experiments each day. You can get rid of bad ideas. You can validate good ideas. You can write loops to tune parameters, and you just progress to the variation of your ideas that actually works much, much faster. And to a large extent, what we've seen in the AI field in the last few years is really, it's sort of like the old parable of you drop something in the street and then you look for it where the light was instead of where you dropped it, right? People are working on the algorithms that are fast on the currently available hardware, whether or not those are the algorithms that actually are the best ones in terms of AGI or the other goals. And what I've been thinking for a while was, well, let's like take the bull by the horns here. Well, we don't want to change our AI paradigm based on the hardware that happens to be available now. If hardware acceleration really is all that, like let's just design and build the hardware for the AGI systems that we think will work. And I was living in Hong Kong for 10 years. I moved back to Seattle, the US, to Seattle area a couple of years ago. But going around Shenzhen and Dongguan, you see it's not that expensive anymore in the scheme of technology business to get new chip designs, you know, at least prototyped and then built in a small production run. I mean, to do large scale production is still an undertaking. So that leads one down the line of thinking, like, what do you need to optimize in hardware based on your AGI architecture? And Rachel had pretty much gone down a similar line of thinking, but more quickly than I had. Of course, having the advantage of starting later in the history of AI. So what we're going to talk about now, Rachel will talk a bit about her plans and designs for hardware optimization for AI methods involving large sparse bit vectors, or so-called hypervectors. And I'll talk a little bit about my design and plan for optimizing pattern matching against large metagraphs, which is the key time-consuming operation in OpenCog and other similar AGI systems. And then as a grand finale, we'll talk a bit about how you might make something like an AGI board by putting together, say, deep learning chip, CPU, a hypervector chip, a pattern matching chip, and whatever other cool AGI algorithm accelerators you guys in the audience may manage to come up with. So yeah, why don't you tell the audience a little bit about hypervectors, why they're interesting for AGI and how you accelerate them in hardware.
Yeah, for sure. Hypervectors is possibly one of my favorite topics, so I could go on forever. But hypervectors are extremely interesting because is this working properly? Because
First of all, what is a hypervector?
a hypervector is just a very large vector that uses real integers, right? It could be complex integers too. But the idea is that you have kind of 10,000 dimensions in this vector. Traditionally, they're filled with either ones or zeros or negative ones and ones, but they could be any real number. And what happens is when you're working in this high dimensional space, because each vector is very large, right? You end up with something that's richer than a field. And that can be debated by different mathematicians. But kind of the idea here is that you get what's called the blessing of dimensionality, which means that you can distribute information over this large space. If you think of like an XYZ axis, and then you multiply that to many, many, many dimensions, one hypervector has a very unique path through that very high dimensional space, right? And so when you take regular information like an image or a sentence or this audio recording or something, and you project it into this or transform it or however into this high dimensional space, what you end up with is something that's distributed. So the information gets distributed over every point in this high dimensional space, which makes it somewhat holographic. That's why when you read about hypervectors, you hear about holographic math. And it becomes very robust to noise, right? So when you have something that's distributed and it's robust to noise, it has fault tolerance, then you have a very interesting tool that acts similar to somewhat how human memory works, right? If you have a heavy night of drinking, you don't wake up and suddenly forget half of the alphabet, things just become a little bit fuzzier from the night before, right? So this distributed property, this robustness to error or noise or corruption is very helpful. And then the other fantastic thing about hypervectors is you can take something like a 10,000 by 10,000 image and compress it into this 10,000 bit representation. And so what Simuli is working on, so what I'm working on in this hypervector chip is this idea of computing in a compressed state. And so when you're computing in a compressed state, you get something really phenomenal, which is you get to use less transistors to compute the same amount of information, which means you're using less energy, which is very good for long-term computing and things like that. So this is kind of the core idea behind hypervectors and why I want to use them and why they're interesting from a computing perspective, in the sense of how can you compute a lot of data at once without constantly needing to slap in more logic and more memory. And I think where this gets really interesting to extend to things like AGI architectures is that if you're trying to have something that understands a little bit of everything or can understand enough to extrapolate to almost anything that's very general, then you need a way of representing a lot of information which fits in a computer that isn't going to just exponentially require more resources over its lifetime. Right, so we need to find ways to take information and represent it in resource responsible methods. And hypervectors is one step in that direction.
Yeah, the way I first encountered hypervectors was in Pentti Kanerva's work on sparse distributed associative memory, which was maybe the 80s or
it was the 80s.
Oh. It was in
earlier.
Yeah, I think it was 1980s. It was sparse distributed associative memory, and Kanerva was pointing out that if a memory that intelligent system has is represented as a very large sparse vector, then associative lookup by pattern completion works better than with many other representations. And a guy named Javier Snyder, I believe, who was a PhD student of Stan Franklin, who organized AGI Conference #1 in 2008. Javier Snyder at one point rebuilt the components of Stan Franklin's LIDA cognitive architecture using hypervectors and sparse distributed memory. It was quite interesting. Then Javier was eaten by Google and went off to do other sorts of things. I don't think they've spat them out yet, or I haven't checked. But I think in my own current work with OpenCog, the sweetest spot I've seen for that is episodic memory. Sort of the memory of the life history of a system is something where you want associative recall. Like you want to say, well, okay, I was riding that, big red bike with the horn, who was with me, right? And you're putting that probe into your memory, then the rest of the episode gets completed. Or if you're an AI system doing biology data analysis over a lot of different patients, you go, well, there was this patient who had gene FKH1 overexpressed, and they were taking metformin. And then you can look back and find other patients who were similar to that qualitatively. Now you can do that other ways. You can do that using logical inference. You can do it using neural nets, but sparse distributed memory, where memories are respected as, or rather represented as, large bit vectors, hypervectors, seem to be especially good at doing this kind of operation. Another likely sweet spot, I think, is inference control, where then your bit vectors represent previous theorems and proofs that you've done. And when you're trying to prove something, you want to find, well, what other proof contexts I encountered in the past were kind of similar, and maybe I should do what I did there. And this is a sort of lookup that a typical memory graph, like we're using in OpenCog, is okay at, but kind of slow at, right? Because if you have a node in the graph, you want to find things associated to it. You're looking in the neighborhood of the graph, and you can do that. You can find everything at distance 1, 2, 3, 4 in the graph, but you're tracing a lot of links, right? And doing a search for similar things to a given hypervector in a hypervector store is a lot more efficient, even if you're just doing it in RAM, an ordinary processor on a computer. Now, if you can massively accelerate the hypervector math using dedicated hardware, I mean, then you're even better off, right? So yeah, I guess we should explain how you ended up diverging or graduating from working on AGI to working on chips, and sort of how does the hypervector chip work?
Yeah, so I'm really interested in this idea of contextual learning or associative learning, right? Which Ben just explained, in which you know some surrounding, like if you're ever trying to remember something, a common thing that you might do is start thinking of other things that were occurring in the situation. So if you're trying to remember someone's name, you might think about like, okay, what were they wearing? What kind of hair did they have? And what's happening, or what some theoretical neuroscientists think is happening in their brain is, and I promise I will get to the question you asked here. So what's happening is that you think that you're starting to activate neurons that are also active at the same time as that person's name was active. And that's in some sense how a memory is stored. And so what you're trying to do is reactivate that pattern of expression, or that the way your brain expresses that information and stores it, so you can recall that memory. And so that process is what I like to call, and other people like to call, like contextual a priori bootstrapping, right? So you take prior knowledge and you bootstrap it to a current situation to help you figure out the current situation. And the current situation could be new, novel, or it could be just something you've forgotten. And so in order to solve this problem, or to kind of work on this angle, I think it's very important to be able to fit a large amount of information into that system, like so to store and learn lots of things without exponentially increasing computer hardware. And hypervectors allows you to do that and process that information at lightning fast speeds, right? Because if you have a vector for someone named Sue, like this isn't how it works in your brain, but you can kind of think of it this way. If you have a vector for your best friend Susan in your head, and then you can remember parts of that vector, all you really need to do is remember things similar to that vector. And if you're in high dimensional space, like in the case of hypervectors, all you have to do is take a distance measure. So it's very fast. It's very quick. The issue where this breaks down on today's hardware is that you're using a lot of fixed point operations, and since each hypervector is very large, every time you need to work with that hypervector, you have to shuffle it around. And our current architectures and CPUs and GPUs and IPUs and things like that just aren't really set up to shuffle these giant containers of bit vectors around, right? You need something like processing and memory. And they're also, I mean, the GPU especially is exceptionally built for floating point operations. And those kind of operations are wonderful and fantastic. But we're already seeing people like GraphCore kind of take what came out as a graphics card, strip away all the graphics stuff, and come up with an even more powerful deep learning card. So if you, going back to our kind of earlier discussion here, if we're talking about like, how do you accelerate the math that AGI runs on, like knowledge graphs or this hypervector thing or something, we really need to have something in which is designed to do that and accelerated to do that, and not be using something that was designed to do something completely else. So that's kind of how I got into this trajectory. I wanted to work on this bootstrapping contextual problem so it can fit into Hyperon or you know, be a part of a more robust human-like AGI. And then I realized that I need hardware in order to use the math I want to use. So that's how we got here.
Yeah. So then the analog of that on my own side was working in OpenCog, in the classic version of OpenCog before we started with Hyperon, the new version we did a workshop on yesterday. When you profile the bottlenecks in running AI algorithms on OpenCog, what you find is almost all of the time it's taken pattern matching against our knowledge graph or knowledge metagraph, which is the atom space. I mean, it's not intrinsically have to be the case. You could of course write in OpenCog something that, you know, solves a combinatorial problem or approximates a differential equation, and then now and then looks up inside the atom space. But that's not what we actually wind up doing for the algorithms. It makes sense to us for AGI, right? What we're actually doing, we're writing code that does a little bit of applies a reasoning rule, or projects a vector, or combines two programs. Then it puts something back in the atom space, and it gets something else out of the atom space graph and does something else. And so the bottleneck is basically finding something in the atom space, which is generally done by pattern matching. You have a sort of template telling what kind of thing you want, and then you grab it out of the atom space. And some of that has to be alleviated by distributed processing, which was Andre Senna's talk yesterday, where you have an atom space graph across many, many machines. But I mean, you can't do everything that way. You have to be able to cache a lot of stuff in RAM on one machine, do pattern matching against the in RAM graph, right? But then if that's slow, then everything is slow. And you start thinking about how do we make that fast? Again, you come down to, yeah, you need processor and RAM, and you also need MIMD parallelism, right? So I mean, in GPU, you have what's called SIMD, single instruction multiple data stream parallelism. I mean, you have just like the Cray YMP I worked with in 1989. I mean, you have a bunch of processors, and they're all doing the same thing at the same time. Then they're all doing the same thing at the next time. They're all doing the same thing at the next time. And that suits matrix multiplication perfectly, right? I mean, on the other hand, say Danny Hillis's connection machine, going back again to the 80s and the deep, dark caveman prehistory of AI. I mean, Danny Hillis's connection machine, which was built with up to 128,000 processors. The one I worked on had 64,000 processors. We were making like 8-dimensional Mandelbrot sets with it and so on, right? But that had the 64,000 processors could each do different things at the same time, programmed in CM Lisp. And of course, the brain is like that. The different neurons are all at different stages and going through the Hodgkin-Huxley type dynamics at each time, right? So you need some architecture which is processor and RAM, MIMD parallel, custom for pattern matching on large graphs, hypergraphs, metagraphs. And I was thinking about this for a while. It seemed like an interesting problem, but a big pain, a big project to undertake. But as technology progresses, it becomes less and less of like an insanely big digression to actually work on custom hardware, right? And the architecture that I finally came up with in conjunction with various folks who know more about hardware than I do. I mean, you can buy little processor and RAM units that are basically like eight processor sandwiches, and they're like eight layer of memory sandwiches rather with processors on each layer. So each of these little 8 processor sandwiches has a certain amount of RAM across the layers, and there's processors that do things there. And you can then make a square array of these little processor sandwiches. And what you basically do is you take a graph and you partition it across the little squares in your array. Then when you want to pattern match against your graph, you just pattern match separately within each little square against the part of the graph that's stored there. But because each little square in the array has its own processor, then you're matching in parallel across the whole graph. And of course, then you have the issue the graph is dynamic, right? So you have to have nodes moving from one point to another in that square lattice, and moving things at that hardware level is quite slow, which you can address in various ways. Like you can make multiple copies of that square lattice. So while some are rerouting, the other ones are being accessed. But the thing is, now you can actually build that by wiring together existing processor and RAM components in a slightly non-standard way. Now, the logic that runs on these processors has to be custom made to put a pattern matcher custom on each component. So there's certainly a lot to do. And then you need code to go back and forth between the graph stored on your chip and the graph that's stored in regular RAM, and then the graph that's stored in your distributed database. But another thing that I liked about this design, it's sort of a fractal micro image of the distributed atom space design, right? Because what you have on the distributed processing level, you take a large graph, you can divide up the pieces among a bunch of different machines. Then you can do pattern matching differently on the different computers, and you have to migrate nodes and links occasionally among the subgraphs on different computers. So now you can do the same thing at the chip level, where instead of among different computers, it's among the different little processor sandwiches that are arranged in an array to make the chip. So it seems they're fairly direct approaches that one can take without sort of boiling the ocean and inventing whole new types of hardware or something. They're fairly direct approaches one could take. And based on my back of the envelope calculations, we could get a couple orders of magnitude speed up in metagraph pattern matching, like we need to do for OpenCog, by moving to this sort of custom hardware, which is comparable to what you get from GPUs for deep neural networks. And I think, of course, it's a lot of work. You wouldn't want to undertake it lightly, and you wouldn't want to reify details of your AGI algorithm in hardware too rigidly, because AGI is a work in progress. But since we've been working with OpenCog starting in 2001 with Novamenti Cognition Engine, large-scale graph pattern matching has been our bottleneck. So I think it's fairly robust, that that's something we need to optimize, just as with hypervectors. I mean, going back to Canerva in the 80s, it's pretty clear. I mean, you want to take similarity-based lookup, you want to take addition, multiplication, and permutation on hypervectors. And if you optimize these operations, then you can make associative memory and various other operations on hypervector knowledge stores much more efficient. So we're looking at kind of like the matrix multiplication example. We're looking at basic operations that have proved their centrality time and time again. And then finally, there's the idea of putting all these together into an AGI board, right?
Yeah, which is probably the more fun end goal of this. And I think also, I mean, when you're thinking about why make hardware for AGI, another thing is like you want the AGI to be able to think quickly, right? If it has these bottlenecks and it can't rapidly think, then how it's going to limit its growth, its trajectory of growth, and how quickly it can evolve. And maybe that's a good thing in some cases. Maybe you would choose to limit some situations, but if it can't even think at the speed at which we think, it will be quite difficult to use it in the ways we want to use AGI. So I guess putting all of these things on one motherboard and trying to break this almost traditional von Neumann way of computing, or at least break the mold, right? Because there hasn't been that many innovations in computer hardware in terms of like, there has been incremental steps. Parallel processing was huge. The GPU was huge. But there hasn't been any like radical redesign of how a motherboard should operate besides like edge computing and AI or something like that, single purpose use cases. But if you're trying to scale an architecture like an AGI, especially like Hyperon or something, right? If you're trying to scale this up, wouldn't you want to be using every possible compute resource you can, right? Not just one chip or one way of computing, one particular form of logic. You want to integrate different types of logic, different types of computation. And so I guess that's the idea of the AGI motherboard, right? Is that you can add things like a, photonic computer processor, maybe even get crazy and put some DNA processors on there along with these.
Well, before we do that, there's the idea of p-bits, which I think are quite interesting. So I mean, quantum computing is fascinating and important and can be integrated with all this, but there's also some novel approaches to putting probabilistic computing at the chip level, which are kind of cool. So basically you can allow the bit operations on the chip to have a certain error by just not tuning them to be that precise, and they can use less power and generate less heat that way if you let them make mistakes. And you can basically use that to do a hardware simulation of probabilistic evaluation, basically. So you're doing, if you have a program that is a CRISP program implemented with CRISP logic operations, if you let the chip operations be noisy, then in effect you're doing probabilistic programming. You're evaluating that program over a certain probability distribution of errors in the inputs and operations. And there's opportunities to do fun things like that also, which don't involve radically new hardware either. They basically just involve tweaking the current manufacture process a little. I think that's a little harder than your initial Hypervector chip or the initial Metagraph pattern matcher, but it's not as hard as making low-cost, large-scale quantum computing, for example.
Yeah, I think D-Wave is pioneering that one. I don't know if it's low cost, but they're certainly pioneering that. Yeah, I think this idea of like, we're not innovating transistors, right? We're just finding new ways in which to use those transistors that are more efficient and more intelligent and can be integrated together to bring out more powerful computations, right? And I think that's kind of the idea behind, I mean, all of these chips and the motherboard too, is that you're just tapping into an integrative power by slightly changing some of the current innovations that we have in hardware, right? I mean, processing and memory is kind of a newer innovation that hasn't really been reliably, stably manufactured for things like memristors. You've probably heard of things like that. So it'll be exciting to see that hitting the computing market here in the next 2-3 years.
Yeah, I think in a way, I'm hoping that the things we're talking about here can be inspirational to others in the AGI world. Because if we look at a first version of an AGI board having, say, GPU type processor tuned for deep neural nets, metagraph pattern matcher, hypervector chip, and a CPU, and you have fast processor interconnect on there. That's a start, but are those the only things that you need? Like, is there somewhere here in this event who's working on different class of algorithms that are optimal for solving different part of the AGI problem, for which there's again a clear way to accelerate that by using a custom chip? Then that may go on version two of the AGI board, right? Because I think it's a big lesson for us all in how GPUs have accelerated deep learning, but in hindsight, that may seem like just the very beginning, right? And the approach we're implicitly taking here is not to try to make like an AGI chip to rule them all. That seems quite hard. I mean, that's sort of what Danny Hulse's connection machine was trying to do, like an AGI computing architecture to do everything. And I think that given the way modern hardware works, that's a challenge I don't currently know how to meet. You'd need hardware that's self-reconfigurable to a degree that isn't currently tooled, right? I mean, it's not physically impossible. Whereas if you can break down your AGI architecture into a set of core algorithms where you know those core algorithms are going to pop up over and over again inside a bunch of different applications and cognitive processes, then you can make specialized chips for each of those core algorithms and connect them together. I mean, then that's in a way, it's a specialized hardware architecture for general intelligence, or specialized hardware architecture for a particular category of general intelligence algorithms and architectures, really. And I think that may end up being a critical ingredient to making the breakthrough to real AGI. Not entirely clear. I mean, the thing is, you didn't really need GPUs to make the deep learning breakthrough, right? I mean, now that after people showed on GPUs what they could do, there's all these papers saying, well, on the CPU, we can do almost as well if we just do this and this and this thing. The thing is, it was the easier, faster experimentation on GPUs that brought people to that point, right? So even it may be that we make the big breakthrough before having custom hardware, in which case you get an even bigger acceleration when that hardware is there. But certainly having a couple of orders of magnitude speed up in your basic, most expensive operations will just allow a lot more experimentation and learning to take place, right?
Yeah, I think that's a really important component, right? Is that you need to be able to rapidly test and develop. And if you're fighting with your system on optimizing on every step, then that slows your development, right? So there's a famous quote, I'm not going to remember it perfectly now, but I think the idea is like develop and optimize later, right? Optimize last. And when you do that, what you end up with.
Premature optimization is the root of all evil.
Thank you. Yes. I said it in a much more casual, but that's the correct.
Yeah, you can tie that in with biblical allegories if you want. But
I don't want to do that, but but yeah. So I think that's kind of the idea here, right? Is that on this quest for AGI, we want to get stuff that's working, and if you're fighting with your system to optimize it, you're just going to be slowing yourself down. What you really want to do is get something that you want to work and then have someone optimize it in a hardware that's optimized for it. And then now you can scale up. And that's not to say you shouldn't think about scaling beforehand. I'll talk more about that later, but on Monday. But I mean, it's important to know how to build, when to optimize, and when to scale, right? And hardware plays a crucial role in each one of those steps.
So what
right?
were the key sort of principles or ideas behind the actual design for the Hypervector chip?
Well, okay, so basically what you're doing is you're taking any data, right? Text, numbers, images, and you're transforming that into a hypervector using a compiler, right? So the compiler is a very key component. There's a measure of kind of like robust immunity. It's not quite security, but it's secure for most general purposes. That's built in just to the hypervector math. So now that you have your compiler on chip has transformed regular data into a hypervector, now that hypervector we want it to live in some sort of non-volatile memory so that you don't have to continuously DMA, or which means just pull data from RAM or hard storage into the accelerator chip, right? You just want the data to be in there because that's what you're working with. And so you need this non-volatile memory. You also need to be able to do a lot of, it's just quicker if you do a lot of fixed point math or just worked with like Boolean bit math, right? So we've made some considerations on the logic to work with this fixed point math. And then you want your memory and your logic to be smacked up right next to each other because these containers, I mean, you can think of a hypervector as like a giant bus, right? Normally you're dealing with an integer, which is like a steering wheel, right? Not a whole bus. So now you're dealing with a whole bus and that bus has to stay together, right? So when you move it around in memory, you want that to be close to logic. So we've adopted a Pim architecture that is kind of just, it's just like a sea of memory really with tiny bits of islands of logic, which are able to have each hypervector has its own logic associated with it. And the logic is basically sitting on top of the hypervector. How many
hypervectors can you fit on the chip?
Well, that's what we're working on figuring out is how many. But I mean, the principle of hypervectors inherently reduces the amount of memory you need, right? If you can fit 100 million image into 10,000 bits, then you're significantly reducing memory required, right? So it doesn't matter. I mean, we should be able to fit a lot of vectors because in a GPU we can fit a lot of regular vectors, right? And so we expect to do at least that much as an NVIDIA GPU or whatever. So by default, you automatically know you're going to be getting a huge memory break, right? Because that's just how hypervectors work. So does that answer your question on design considerations?
Partially. Probably about as well as we can do with that.
If I had some graphs and maybe
yeah, probably about as well as we can do with that with just words. Yeah,
I think it was super clear.
All right.
Thank you.
So how do you see this fitting in to your overall quest to build AGI? Like once you have the hypervector chip done, then how do you get a thinking machine to pop out?
Well, I just hand it over to you, right? And you plug it into Hyperon and
there we go,
and
yeah.
that's
Well, we can definitely use it for episodic memory and inference control and a bunch of other stuff in Hyperon. I think it also could be an interesting alternative to matrix-based accelerators for some neural net or computational neuroscience simulations as well, which you've talked about a bit.
yeah. So the hypervector chip, which we're calling the NDPU, in case anyone wants to look it up on our website. Basically, what we're doing is we're democratizing hypervectors for general hyperscale computing, right? So we're tackling something that is not domain specific to AGI, but I think that's an important first step because scaling is really important to think about before you start building, right? You don't want to be constrained by something that cannot grow. If you plant seeds that can't grow, it's an issue, right? And so kind of on this bigger AGI trajectory, to answer the question a little bit more seriously, there's an idea in theoretical neuroscience from Andrew Coward called the recommendation architecture, which has, whether or not it's true, right? Whether or not it's a true model of the brain or whether it needs to be a true model of the brain
It's true and not true.
It's true and not true, right? It's very consistent. So the idea is that if you want to self-activate or if you want to use contextual bootstrapping of prior knowledge, then you need to keep some sort of record of what occurs at the same time. And if the most naive and horrible way to do that is to just write down things that occur together in pairs, and your list will grow continuously and very, very large over the course of just like 30 seconds, right? But if you use hypervectors, then you can get this combinatorial like explosion in which you can keep a record like this much more efficiently. And we're getting very technical now into the details, which maybe I should explain it at a later time. But the idea here is that you're compressing information. So let's just think about them as memories, right? But it could be anything. You're compressing information into this smaller state, and then you're distributing that information and integrating it with other information so that things can be used like Lego pieces. Right. So if you have a red Lego, it's just like the 2x3 little Lego thing, you can use that in thousands and thousands and thousands of different creations for whatever you're building with Legos. And you kind of want the same expression if you're trying to work with how you're representing information. Right. And so this is how the brain works. Right. Is that you have this combinatorial like explosion of ways in which you can represent patterns of activation. And hypervectors have this same property, the same combinatorial explosion property, where you can take information, and I like to call it multiplexing. You can multiplex it out into many different scenarios. And I think that will be important for generalizing. But like I said, we're tackling this scaling issue first before we get into
Yeah. But I think, you know, that there's with both the hypervector chip and the pattern matching chip and the whole OpenCog Hyperride infrastructure for that matter, there's general purpose tooling being built, and then there are particular sort of cognitive science / AGI system hypotheses that can be explored with that tooling. And I think it's important that something like the hypervector chip, NDPU, we could use it for episodic memory and inferential memory in OpenCog. You could also use it as a more efficient way to implement certain sorts of neural architectures, right? Since I mean the neural nets are sparse, they're not dense matrices, and for many purposes the hypervector store is a more efficient way to represent the sparse memory operations than a matrix, which is being taken into account in different ways in standard deep learning chips. But the hypervector approach is quite interesting. I mean, in a similar vein, I was chatting with some folks from the NARS team about. I mean, you could take the NARS AGI, the NARS inference rules anyway, and NARS chunking heuristics, and it wouldn't be terribly hard to implement those in Meta and to use the OpenCog atom space to store that. That's a different sort of AGI theory in a way. It's a slightly different cognitive architecture, but a lot of the tooling could still be used. I mean, just like with TensorFlow, you can build all sorts of different neural architectures and see which one you like best. It may not be one that Google ever thought of. So I think this sort of AGI board can be very valuable for our own research, jointly and individually, but I'm hoping that it's optimizing algorithms that are abstracted enough that it could be useful quite widely for people exploring all sorts of different ideas also, as has been the case with the accelerated matrix multiplication hardware.
Right. Yeah. The goal is not to have another like edge AGI device, right? That's not the goal, is to just concrete and cement the algorithms and operations into the hardware. The goal is to have a hardware architecture that can accelerate the shared principles of computing. So like Nelson's talk is very interesting in this context, right? Of like, what are the shared processes which can be sped up, which aren't being sped up?
Well, what that sort of math can be used for, among other things, is to help transform diverse cognitive processes into the forms that can be directly optimized on chip, actually. But I think we have to optimize our time now, and we have used our allotted slot. I don't know if we have time for a few questions.
We'll take just one, if there's one burning question from the audience. And then what we're going to do, we're going to email out our Discord link. We've got 2 questions online and we'll have the discussion we'll keep going with the questions on the Discord link. Have we one desperate burning question from the room? Joe.
Hi, I've got 1.5 questions, but the half question is pretty stupid, so you can answer it quickly. And that one is, have you guys thought of making a bread computer where it does its computation when you bake it? Might be plausible. The other one is, could you say more about how, it's confusing to me, how you can break down large pieces of data into smaller parts and retain all of the complexity? Like, how can you take a picture that has millions of pixels, put it into a 10,000 bit vector and retain all that?
Good question. Thank you, Joe.
I can let you take the bread question. The second question was more on hypervectors. So Pentti Kanerva has some wonderful slides. He works with UC Berkeley that can kind of walk through how this math happens. When I first heard about it, it sounded very magical too, right? It sounds magical.
I mean, you
You're
can't
like,
do lossless compression of a billion bits into 10,000
well,
bits.
yeah, I mean, we've found some ways in which to do some interesting tricks to make things lossless. I'm currently working out with some very bright professors on the information theory limits and how that works out. Yeah, but yeah, in general, hypervectors are not meant to be lossless. So they're more meant for analysis. So you're just working with some sort of symbolic, it's pretty symbolic, maybe not in the sense that the word is typically used, but you're just working with an analogy of the information and rather than the information itself.
Well, for example, if you're looking at an image search application, then if you do the mapping into hypervectors effectively, you can get a very massive degree of compression. It is lossy, but it will give you a very low error rate in image search queries. I mean, as one particular example.
Okay, we're going to wrap you up there. Thank you very much indeed, both. It's fantastic to see the entire infrastructure of the post-singularity, this is pre-singularity.